Week 10. In this week's videos, we're going to talk about what a directional derivative is from Kali 2.6. And so you can see we have 5 videos. Just a note, if you're looking through the textbook, we are not going to discuss the implicit function and inverse function theorems. If I remember correctly, we do come back to those in the spring. Okay, so since we're talking about directional derivatives, might as well define them. The idea here is that our previous definitions of derivatives have focused on partial derivatives when we were talking about multivariable functions, but now in general, we might not always be traveling along the x or y direction only, right? We could do a combination of those, or we might have along or in space that is 4 dimensions, and so we might have, x, y, and z directions, and then also a 4th direction. So we want to be able to discuss how a quantity changes along different axes. As well as other directions that are combinations of those axes. Okay, so definition here. We have a function defined on n space, so it has n inputs and one-dimensional output. Okay, we have a point in that domain D. Okay, and v just being a vector in n-dimensional space, but it does have to be a unit vector. Okay, so if it is not, make sure to change it so that it is. Okay, and then we talk about the directional derivative d sub v, and just keep in mind this is not meaning the derivative matrix. Okay, so d here does not mean the derivative matrix, and that is defined as a limit which looks oddly similar. And the idea here really is extending that definition from one variable calculus that we saw already. So this is just saying take a little teeny tiny bit of that unit vector and add it to our point and see how the function changes, and that's the idea of a directional derivative at a in the direction of that unit vector v. Okay, so then maybe you're wondering, well, why is this okay? Why can we do this definition? Okay, so let's take a look. So if I just restrict myself to two-dimensional space and I say v is the unit vector in the x direction, okay, that's fine. And then, let's talk about the derivative of I, right, at any point a, b, okay, and so this would be, by definition, the limit as h approaches 0, and then we would have f of a, which is my point AB, I'm just not writing it out, plus h times the vector 1, 0. Okay, and I should probably put that in angle brackets, okay, just to denote that it is a vector, and then close parentheses minus f of a, all right, all over h. Okay, and then if I expand this just a little bit, this is going to be the limit as h approaches 0, and then I have f of, and then this is going to be a plus h, adding those respective coordinates, comma, and then b, b, okay, again, so here I'm taking a to be the point AB, or the vector, okay, and then we have to subtract off f of AB, right, and then I believe if you look closely enough and remember carefully, this is really just the partial derivative with respect to x at point AB. Okay, so really what I'm saying is that the directional derivative along the x-axis, using the unit vector in the x direction, is really just the partial derivative of f in the x direction. And so similarly, we would say the partial derivative of y is defined similarly. So this definition really is just a generalization of a partial derivative. Of partial derivatives. Okay, so that's kind of why we can do all this and talk about directional derivatives. Now, just as another quick example, let's see here. Here's my example. Okay, so we've seen this sort of surface before. Okay, and I give you a point and find the directional derivative in that direction. Okay, so right now we're just going to use the definition here. So I do limit. Okay, notation-wise, I should do d sub u, okay, I'll define what u is in a moment, at the point 1, 1, okay, is equal to the limit of, or as h approaches 0, of f of 1, 1 plus h times, and now I should really put that u in there. I'll leave a space for it in the time being, and then plus, or minus, f of 1, 1 all over h. Okay, so now the reason I left the space there was because remember that when I was talking about my directional derivative, I need that vector that I'm looking at the direction in needs to be a unit vector. So really, if I have this as v, I should say that u is, well, divided by the magnitude, 1 by square root 2, 1 by square root 2, okay, and so then I can insert that 1 over square root 2, 1 over square root 2, okay. And I'm going to encourage you to pause the video and catch up on the algebra. What I got after doing a bunch of algebra was that this is going to equal negative 2 square root of 2h over h, okay, which you can cancel h's, just get minus 2 square root 2. Okay, so now let's see how that is visualized. Okay, so there is a GeoGebra file that you can access in our Google Drive folder, and if you open that up, you get to visualize the surface, and there is our point A, right smack dab in the middle there, and you can rotate it per normal. Okay. So again, just as a reminder, if you were to hold x constant, that is to say to enable this plane that I have labeled as B, and then if you enable G is going to be the line that is tangent to the surface when x is constant, so that's as y changes. And that's just a line that a tangent line created using the partial derivative with respect to y. Similarly, if you enable C and F, that's again holding y constant, and then so the line that is being visualized is tangent to the surface at that point as x changes, so that's created using the partial derivative with respect to x. Okay, so now here's the grand finale. If you enable plane E, okay, so this is the plane x is equal to y, which is our coordinate, right? 1, 1, x and y are equal, so the point should lie on that plane. And then if you create a tangent line using the directional derivative now, you can create that tangent line here, and this would be the line that is tangent to the surface in the direction of our unit, in the direction of our unit vector 1 over root 2, comma 1 over root 2. Okay, so that's kind of interesting. So just as we talked about partial derivatives with respect to x and y, we can use a directional derivative to talk about the derivative of a multivariable function in any direction, as long as we're talking about it using a unit vector. And that's going to be the end of this video. Next video we get some nice algebraic simplifications.